The next speaker in the session is Raphael Saavedra, who is going to talk about unlocking reserves with smart transmission switching. Raphael has received his bachelor degree in electrical engineering from the Pontifical University of Rio de Janeiro and a master's degree in electrical engineering from the same institution in 2019. He has worked at the Laboratory of Applied Programming and Statistics and is currently at Invinia Labs in Cambridge in the UK. Raphael, the floor is yours. You will be presenting live.
Sorry, I had to unshare my screen for it to work. Let me try again. Okay, can you confirm that you can see my screen and that you can hear me?
We can see your screen. And
okay.
Yeah.
Okay, so I will be talking about unlocking reserves with smart transmission switching. I'm Raphael. I am a researcher at Invinia Labs in Cambridge, UK. This is work done mainly during my master's at PUC Rio, and this is joint work with Alexandre from PUC Rio and with José Manuel Arroyo from the University of Castilla-La Mancha in Spain. First, let's start talking about what is transmission switching. Transmission switching is simply the act of opening a functional line or closing an open line. Why would you open a functional line? Well, the idea is that because of Kirchhoff's voltage law, each closed loop in a system is an additional constraint to operation. So by opening a functional line, you can reduce the number of loops in the system, and therefore you can alleviate the system operation, which can make big differences. First, let's look at power system operation from a two-stage approach, which I'm sure lots of people are familiar with. First, we have generation scheduling, then we have uncertainty occurring, and then we have corrective actions to minimize the harm done by those uncertainties. When we talk about generation scheduling, we usually are talking about the optimization of energy and reserves. We can also have transmission switching in this stage. When we talk about uncertainty, we mainly talk about load because obviously load is not perfectly forecastable. We can talk about contingencies, we can talk about renewable generation, etc. And when we talk about corrective actions, we are mainly talking about the generation redispatch with the use of the reserves that were allocated in the scheduling stage. And also we can also have transmission switching at this stage. So in the literature, transmission switching appears mainly in two different ways, which we call preventive and corrective switching. So when we talk about preventive switching, we're talking about switching that is conducted at the time of the generation scheduling, and that affects only the base case. So this is common in papers related to unit commitment, for example. So the idea is that when you are running your generation scheduling, when you're co-optimizing your energy and reserves, you also run an optimal transmission switching problem that can either be co-optimized with those or not, and then you adjust your system topology in the base case. And regardless of the consideration of contingencies, only the base case is affected. Now, when we go to corrective switching, this is a very different approach, and this is more common in papers related to contingency analysis, for example. What happens is that given that a contingency has occurred, or given that a certain uncertainty has occurred, we can find the optimal new topology for the network, considering that the loss of that unit or whatever has happened. So these are two very different approaches. And the problem here is that these are not closed loop models. So the idea is that even if you consider the optimal corrective switching action with respect to a contingency, you did not consider that you could do this action when you scheduled your generation and your reserves. So this is an inconsistency, and this leads to suboptimality by definition, because you're including a feature in the corrective stage that was not explicitly considered in the model in the generation stage, in the generation scheduling stage. So the idea of this work, the main idea of this work, is to just close this loop. We want to propose a framework where we, when we are scheduling the generation, we are considering preventive transmission switching as has been done before. And when we have the corrective actions, we are considering the corrective switching as has been done before. However, the main difference here is when we are considering generator scheduling, we are also considering the possibility of the corrective switching in the corrective stage. So this will affect the scheduling in the first stage. So this is our formulation. There's lots of letters and symbols, but the idea is pretty simple. We are minimizing the cost of energy reserves and worst case power imbalance. We are considering a DC power flow model. We are considering contingencies according to a security criterion, which in the case of this work will be n-1. We are considering reserves and we are considering ramping. So there is also intertemporal constraints in this case. And most importantly, we are considering pre and post contingency transmission switching, which appear in the form of a binary variable. So the idea here of the solution methodology is that if we try to solve the problem with the direct application of off-the-shelf commercial solvers, for example, if you just take the Gurobi and try to solve this problem, it won't work because this is a challenging problem to solve for several reasons. We have ramping, so there's intertemporal constraints, there's binary variables coming from transmission switching, and perhaps the most important, well, this is a contingency constraint model. So because it's a contingency constraint model, we need to take into account, we need to formulate the operation under each contingency state, which leads to all these, let's say, kind of repeated constraints, one for each post-contingency state. So the idea here is to use the decomposition technique to iteratively solve the problem. So in the literature, this appears quite often, either in the form of Bender's decomposition or column constraint generation algorithm, which I will just call CCGA for short. And here we will use the CCGA. So the idea is to identify the worst contingencies and iteratively add them to the model. And in this way, only a small subset of contingencies actually needs to be considered. The problem with this approach is that the CCGA, the standard CCGA in the literature, it relies on the dualization of the lower level problem, which in our case is the generation redispatch with optimal corrective actions. However, because transmission switching is modeled with binary variables, we have binary variables in this lower level problem. So this is a mixed integer problem. Therefore, we cannot dualize it. So the solution is to use what is called the nested column constraint generation, which was proposed by Zhao and Zhang in 2012. And the idea is that we have some transformations to define a CCGA within the CCGA to solve that subproblem, which is kind of challenging to solve with that it cannot be solved with the standard CCGA. And same as the standard CCGA, the nested CCGA is guarantees optimality in a finite number of iterations. So that's pretty good. The algorithm is like this. So we have a master problem, which is simply a relaxation of the original problem, where only a subset of contingencies is considered. So in the first iteration, we just completely disregard contingencies. We just solve the base case, and we get a optimal schedule for that scenario, for the base case only, which is, of course, not what we want. It's a lower bound. It's a lower cost because we're not considering a lot of constraints. Then we get that schedule that was output by the master problem, and we run the subproblem, which aims to find the worst case contingency with respect to that schedule. In order to solve this subproblem, we need to compute that inner loop, which I will not go into detail right now because of time. But we have then an inner loop, an inner CCGA loop that iteratively solves this subproblem and outputs the worst contingency case for that generation schedule. Now we increment the contingency set of the master problem with this new contingency. And then we run it again, we get a new schedule, we run the subproblem again, we find a new worst case contingency, so on and so forth. And it's easy to see that eventually the master problem will simply become the original problem. But the beauty of this method is that you don't need to consider lots of contingencies for this to happen. You can converge with only like a handful of contingencies, which makes a significant difference in computing times. So for numerical results, we used two systems. The first is a 4-bus example system that is presented in the slide. And that is just for illustrative purposes. And the second one is the IEEE 118 bus system. We used 50-minute periods in 1-hour windows for 24 hours. So basically, we considered the whole day, 24 hours, and for each hour, we ran economic dispatch for the following hour, which is equal to 4 50-minute periods. And we used a typical load curve that is common in power systems. And then we compared 3 different approaches. The first approach is no TS, which is a model that just completely disregards transmission switching. It's just a regular continuously constrained economic dispatch. The second, which is called SEC-TS, is a sequential approach. It includes both pre and post continuously switching, but they are not co-optimized. So as discussed before, the idea here is to consider both preventive and corrective switching actions. But in the generation scheduling stage, there is nothing in the model saying that when the corrective stage comes, we will be able to alter the topology. And then there's what we call Smart TS, which is just a model that co-optimizes both pre and post continuous switching together with energy and reserves. So for the 4-bus system, of course, these results are a little bit unrealistic because the system's super small, but it's just to give an idea of the impact that this can have. So when we look at the first row, this is very early in the morning where the load is very low. There's absolutely no difference between the 3 approaches. But when the load gets high and the system gets under stress, no TS has a significant worst case power imbalance. And the sequential approach still has a lot of power imbalance. When we go to Smart TS, this power imbalance is completely nullified. And it's a striking difference considering that the sequential approach and Smart TS have the exact same features. The only difference is that in the sequential approach, they are not optimized. And why does this happen? Well, this table shows the allocation of reserves in the generation scheduling stage for each 15-minute period in that peak hour. And we see that Smart TS unlocks more reserves, more upspinning reserves than sequential TS. And why that happens? Well, it's not like the sequential approach doesn't want to unlock more reserves. What happens, in fact, it would gladly unlock more reserves if that prevents imbalance, because in our formulation, balance is the most expensive thing. What happens is that because the operation can be constrained and we need to modify the topology to unlock certain aspects of the operation, because the sequential approach doesn't know that we will be able to modify the topology in the corrective stage, it cannot allocate more reserves because it thinks that these reserves will simply be constrained, they won't be used. So what happens is that it just doesn't allocate more reserves than the amount of reserves that would be ideal. And Smart TS is able to unlock those reserves, and that makes the difference between having and not having power imbalance in the worst case continuities. For the okay, I'm about to finish. So for the 118 bus system, we see here the results for each of the 24 hours. And similarly to the 4-bus system, in the cases where the load is low, there is absolutely no difference between the costs. But when we go to the peak hours, there's a big difference in system costs. And this difference is basically because of the worst case power imbalance. So we can see that in no TS and sequential TS, there is significant power imbalance in the peak hours. And for Smart TS, the system is capable of having no power imbalance at all during the whole period. And I'm sorry, the slides are going alone, I don't know why. So the Smart TS is able to have 0 power imbalance throughout the whole 24 hours. Additionally, I just want to mention that we also have extended this analysis for unit commitment, and we have used other features such as renewable generation, energy storage, a larger system, and out-of-sample analysis. And this paper has just been accepted and will be, I think it's already available online. So please check it out if you're interested in. And these are the references and my contact if anyone wants to follow up with questions. Please feel free to do so. Thank you.
Thank you, Raphael, for a very nice presentation. If Kentan is in the audience, he may have some questions, but for the moment in the Q&A, I don't see any questions coming in. So maybe I can pose one myself. The cost that you presented in the table where you were also showing the load shedding in the course.
Yeah, it does include the power imbalance.
The costs themselves include the load shedding?
Yeah, there is a term here, this CI times phi includes the power imbalance. And this is because first we want to ensure that the problem will always be feasible. And second, because we want to be able to model the cases where power imbalance is present. So we want to be able to compare those.
So in table 11, the numbers include, sorry, in slide 11.
Yeah.
Oh, sorry, no, yeah, whatever it is.
You
No,
mean
that's not.
in the results? Yeah.
In the results, yeah.
Yeah. So the difference in system cost. This is something that we explore better in the paper as well. The difference in system costs here, of course, this is simply the value of the objective function. So the difference here is mainly due to the difference in worst case power imbalance. When you look at the actual operation costs, they are somewhat similar. So in the end, the idea is that we have similar costs with greatly increased reliability.
Right, okay, really interesting, thank you. Shab Degan asks, thanks for your nice presentation. How many transmission lines are considered as switching candidates in the IEEE 118 bus test system? Yeah,
that's a very good question. So choosing the set of switchable lines is something that is hard to do. We have to do heuristics in this case because optimizing that at the same time of the operation is it's completely unrealistic. So what we do is we run offline studies based on the load, and like we have something like an expected load, and we run an offline study to find which are the best couple lines to do that. And in the 118 bus, I think we used 5 switchable lines. So it's also interesting because these studies show that with a very small set of switchable lines, you can already achieve as good a result as if all lines were switchable. So you don't need to consider all lines as switchable. You can have just a small set that can be defined in offline studies.
Yeah, I think O'Neill had observed that quite a while back, but it applies here too. Yeah. In this figure, you're essentially showing a system that is more reliable and cheaper at the same time.
Yeah, so like I said, the system cost here is just the objective function of the problem. So it can be a little bit misleading if you think about operation costs. The differences are mainly because of the worst case, the cost of the power imbalance. The system costs are not higher when you consider switching, but they are similar. If they are lower, it's a small amount of reduction in. So the main benefits here are reliability for sure.
Okay, and just for the recalling the intuition, because so in Zhao Zhang's algorithm, I'm just continuing. We have a new one, so I'll stop. Mm-hmm. Patrick Panciatici asks, great presentation. Could you clarify if you take into account uncertainties, could you extend this to substation reconfiguration, bus merging, splitting?
In terms of uncertainty, in this particular work that was submitted to PSCC, we only consider contingencies, but in our other extended paper, we have considered the uncertainty coming from renewable generation, from energy storage as well, and there's you can consider pretty much anything that can be used in this case, we used a robust formulation. So, for example, load uncertainty as well, you could use. About the remaining of the question, I am not so sure. I am not super familiar with those formulations, but I will be. I'm glad to continue that discussion offline if needed.
Great. So I'm sure Patrick can find your information and follow up. Maybe I'll squeeze one last question into the session. David Pozo asks, transmission switching usually brings benefits in heavily congested networks. Probably is not the case if it is not congested. Do you have intuition about it based on your experience? Yeah, so this is basically what we show here. Like when the system is not under stress, either considering our no TS or a sequential approach or a co-optimized approach, they all have basically the same result.
as soon as you start having a heavily congested system, that starts to change. So I think that's basically it. The idea is that this is relevant when you have a system that is heavily under stress. And of course, this stress can come from outages or from heavy load uncertainty, etc.
Noted. Thank you, Raphael, for a great presentation.
Thank you.
And we move to the last speaker.